Hello, and welcome to my talk on semantic image fuzzing of AI perception systems for ICSE 2022. My name is Trey Woodruff, and I am presenting on behalf of Sebastian Elbaum and Kevin Sullivan of the Lab for Engineering Safe Software at the University of Virginia. Today we are going to talk about testing autonomous systems. First, let me introduce the concept of semantic coverage. Semantic coverage is the notion that our autonomous systems should be validated on the set of possible scene semantics that could possibly occur in the real world. For example, here we see a common traffic scenario that our autonomous system might encounter, a busy highway. Test suites for autonomous systems contain many tests like this one to validate the performance of the system. And this is good, because we need to ensure that our system will behave safely in this scenario. However, there are many semantically different scenarios that are uncommon and not available in the test suite used for these systems. Consider this example. Our autonomous system is approaching an overturned vehicle in the roadway and needs to proceed safely. While this is highly uncommon, the system's performance in this case is still safety critical. In this way, we see that testing for autonomous systems necessitates achieving high levels of semantic coverage of the possible real-world scenarios. Let me lay out the vision for this work. Existing autonomous system test suites achieve poor semantic coverage. This creates safety hazards due to misinterpreted data, and current methods to increase semantic coverage are limited. Thus, we introduced the idea of local semantic test case mutation. By applying correlated mutations to real-world input and expected semantic output, we generate realistic and novel test cases to expand semantic coverage. Our experimental results show the ability to uncover perception failures in state-of-the-art systems. First, let's take a step back and examine the autonomous system pipeline as a whole. Autonomous systems operate in the physical world using sensors to generate readings of their surroundings. Then, the perception software takes in these readings and generates a semantic interpretation that the autonomous system will use to inform its action in the physical world. In this talk, we are focused on testing the perception software due to its critical performance in ensuring the correctness and safety of the system as a whole. The perception software takes the sensor reading as input and produces an interpretation of that input to inform its action moving forward. These are the input and output pairs when testing the perception system. Here we see an example test case for the perception software. On the left, we have the image produced from a dash-mounted camera of an autonomous vehicle. On the right, we have the semantic interpretation of that image, in which each of the pixels are labeled based on what object they represent. For example, the road is purple, the sidewalk is pink, and the pedestrians are red. So why do we need to focus on the perception software for testing? Autonomous vehicles are safety-critical systems, and perception failures have led to fatalities. For example, this Tesla was recovered from a fatal accident in June 2016. According to Tesla, neither autopilot nor the driver noticed the white side of the tractor-trailer against a brightly lit sky, so the brake was not applied. This showcases how an error in perception can lead to safety-critical errors in the system as a whole. Our technique generates novel perception test cases at a low cost that extend coverage of real-world semantics in a realistic way. As an example, and to set the stage for the rest of the talk, here we see an example of how our technique can perform a local semantic mutation to an existing real-world test case. On the left, in the original test case shown previously, we see a mostly empty roadway. This provides a useful but not very challenging test case for the perception system. On the right, our technique has performed a local semantic change by adding a new vehicle to the roadway, and it does so in both the test input and expected output. In this way, our technique has generated a realistic test case that covers a new, semantically different scene. Now let's take a step back and examine the three main approaches for testing autonomous systems. The first category of testing uses real-world data. There are several available datasets, including Kitty, New Scenes, and Cityscapes. Real-world data is the gold standard for autonomous vehicle validation, as it contains a snapshot of what the system will see when it is deployed in the physical world. However, this comes with two major limitations. The first limitation is cost. These data are very expensive, both in the cost to collect the data in the physical world and the cost of human time to act as the oracle to generate the expected outputs of the system. The Cityscapes dataset reported that generating these high-quality annotations required over 90 minutes of human effort per image. The second limitation is the scope of the data. These test suites are limited in that the scenarios available reflect the scenarios that occurred during the collection time, which represent only a minuscule fraction of the possible driving scenarios. While these test suites cover at most a few thousand miles of driving data, a study by the RAND Corporation found that autonomous vehicles would have to drive hundreds of millions or hundreds of billions of miles to demonstrate reliability on a human scale. The next category for testing is the use of simulation. This decreases the cost and increases the scope, and prior research has examined ways to leverage simulation to explore rare scenarios. However, the use of simulation introduces the weaknesses of the simulation reality gap. The simulation reality gap is a well-studied phenomenon that details how, due to differences between the simulation and reality, failures found in simulation may not generalize to the real world. As such, autonomous vehicle companies such as Waymo have found that while simulation is a valuable tool, the results must be revalidated in the physical world. The final category, which includes our approach, aims to leverage existing data through mutation to expand the suite of available tests. By mutating existing real data, these techniques aim to fall on the reality side of the simulation reality gap. Let us now take a closer look at several of the prior techniques for mutations. These come in three main categories. The first is data augmentation techniques. These techniques, including affine transformations and adding noise, are widely used in machine learning as a mechanism to increase the robustness of the system. However, these techniques do not consider scene semantics and thus generate data which is not suitable for testing. The second category are global semantic mutations. This is a line of work that tries to interpret the semantics of the scene as a whole and apply mutations that incorporate how these scenes would be encountered in the real world. For example, these techniques add fog, rain, change the brightness, or even do more sophisticated weather mutations such as adding snow to the ground. This image shows an example of adding smoke or haze to a scene. These techniques are an important step in validating these autonomous systems, but they do not consider the local semantics of the scene, which limits their overall utility for increasing semantic coverage. And finally, we have semantic data augmentation. This line of work examines how to leverage the learned semantics of the latent space of the system in order to perform semantic mutations. This has been applied to machine learning contexts outside of the autonomous system domain, and primarily to system training rather than testing. For example, prior research has taken a picture of a person using a facial recognition system and used the learned latent space to add glasses to the person. This is very expensive because it requires human identification of the latent space, and there is no guaranteed realism of the resulting output. Additionally, we do not control what features are learned in the latent space, limiting the generalizability of this technique. This is where we come in. We want to combine the best of all of these techniques to perform local semantic mutations on real data while ensuring that the resulting test case is also realistic. For example, here we interpret the scene semantics and identify the red car, which we then perform a local semantic mutation on, resulting in a blue car. Additionally, we can be even more sophisticated, in this case adding a car to an empty roadway. Generating this test requires understanding the local semantics of the car as well as the roadway in order to ensure that we generate a realistic test case. This results in a novel test case that expands the semantic coverage of the system, in this case showing how the autonomous system would respond to the presence of another vehicle. So what do we want to do? We want to start by leveraging existing data that we can use without incurring the expense of gathering the data ourselves. Further, because this data comes from the real world, we can bypass the pitfalls of the simulation reality gap. And then we want to use semantic mutations to leverage the known semantics of prior data to generate scenarios with local semantic changes while ensuring these scenarios are semantically valid. Doing so will allow us to generate novel scenarios not present in the initial test set, increasing semantic coverage. Let us now examine how this technique works to leverage the prior dataset by looking at an example using the open roadway from before. If we select this initial test case as the basis for mutation when trying to add a car to the road, the system must then find a car suitable for addition. To do so, the technique leverages the available data and searches for a car that would be suitable for addition. In this case, it selects this image as the source for the car. The technique then isolates that car, being mindful of its local semantics, including its position and lighting. It then checks these semantics against the semantics of the roadway, where we plan to add the car, and verifies that they are compatible to ensure the resulting test case will be realistic. If the check is successful, the technique then combines the two to form a new test case. We will now briefly expand upon this idea by examining the full pipeline of our technique. Full details are available in the paper, and a Python implementation is available on our GitHub, linked here. The pipeline begins with the developer specifying the mutation parameters to use during test generation. For example, the developer could say, "We don't have much data for pink cars. Let's change the color of cars to be pink." Or they could say, "We know the system struggles with brightly colored cars, so let's generate new tests by adding bright cars to existing scenarios." First, the system is going to look through the prior data set of real data. In our case, we use the cityscapes dataset, but many other datasets could be applicable based on application. Importantly, not only does this data include the sensor readings, but it also includes the human annotation of the ground truth semantic interpretation. Next, the pipeline is going to do a pre-processing step where it searches through the entire dataset and builds a library of available resources, including their semantics. For example, it is at this step that the pipeline identified the car we saw before as an available resource for mutation. After pre-processing, the system examined the mutation at hand and the prior dataset to select the initial test case that will be mutated. This selection is based on the mutation. For example, if the developer specified to change the color of the car, the initial test case must have a car to recolor. Or if the developer specified to add a new car to the scene, there must be a portion of the road available for the new car. After the initial test case has been selected, the pipeline queries the list of available resources for a list of those that are suitable for the selection in this mutation. For example, in the add car mutation, the pipeline could select the car we identified earlier. Once the initial test case and resource have been selected, the pipeline must ensure that these resources can be combined in a way that produces realistic output. We call this step conformity checking. The goal of conformity checking is to ensure that we retain the realism of our data with respect to the physical world. We accomplish this by designing post-operation checks that guarantee that realism is respected. The considerations for this vary based on the mutation, but the main idea is that we only need to validate the parts of the image that change, and we can use domain-specific knowledge to craft validation rules. Ensuring that the new test case is realistic is a crucial part of the pipeline, as not doing so can lead to false positives where the perception system fails on a test that could not occur in the real world, similar to the simulation reality gap. Let us take a look at two examples of specific considerations for realism we explore in the paper. On the left, we see a brightly lit car that has been added to a shaded street. This is not realistic due to the inconsistent lighting, and thus we added checks to ensure that the added car has similar lighting to the road area where it's being added. On the right, we can see a silver van that has been added on top of a red truck. This is clearly not realistic because the two would be colliding in the real world. While this looks obviously incorrect from the end result, determining whether two objects would overlap based solely on their images is non-trivial. Because of this difficulty in ensuring realism, we have to make trade-offs between how many mutations we can create and the false positivity rate. If we over-approximate realism, we may severely constrain the number of tests that we can generate. However, if we under-approximate realism, the system may generate large numbers of false positives. Further work is required to explore this trade-off to find the right balance. Finally, once the pipeline has decided that the resulting test has passed the conformity check, the new test case is generated. Note now we have a full-fledged test case, including both the test input and expected output. Let us then examine one of the methods for testing a perception system using our technique. First, we have an initial sensor reading R. This sensor reading comes with a ground truth interpretation provided by the human annotation. The pipeline performs the add car mutation to the sensor reading to obtain a new sensor reading R prime. The pipeline then also performs the same mutation on the interpretation of the original test to obtain the interpretation of the new test case. In the new test case, we now have an input and expected output pair. To test the performance of the perception system, we run the perception system on the new sensor reading, for which it will output an interpretation image as shown in the lower right. We can then compare the expected output that we obtained from the mutation with the actual output of the system. In this case, it looks like the perception system did a pretty good job. Now let's take a look at our experimental results. To examine our mutation pipeline's ability to test perception systems, we explored three mutations. First, we examined the mutation to change a car's color as we saw before. We also explored the mutation for adding a car to a scene as we saw in the pipeline example. Finally, we also explored the mutation for adding a person to the scene. I want to take a step back here and highlight one of the key advantages of our approach using local semantic mutations. This is a very important test case. We know that in the real world, autonomous systems may encounter pedestrians in the roadway, and it is imperative that the system be able to accurately detect this scenario to ensure safety. However, we can never run this test in the real world. We cannot put pedestrians in harm's way in order to gather this test data for validation. This is where our semantic mutation technique comes in. By mutating the existing data, we can create these novel scene compositions that are critical to improve semantic coverage of our test suites, but impossible to otherwise obtain. Now let's examine our research questions. We examined three research questions which we discussed in the paper, and I will cover two of them now. For the first question, we examined how effective our technique is at uncovering inconsistencies defined at different levels of severity. We will discuss what this means in just a moment. Additionally, we examined which of the mutations were the most effective. As we noted before, the pipeline produces a complete test input and expected output pair that can be used to directly test the system. However, in this case, we are particularly interested in judging how effective the mutation itself is at impacting the system to uncover failures. Thus, we instead calculate this drop metric, which calculates the performance of the perception system on the original test case, and then subtracts the performance of the system on the mutated test case. Accordingly, any decrease in performance was directly caused by the mutation. We refer to these drops as inconsistencies in the performance. We examined 3 levels of increasing severity for the inconsistencies. A moderate inconsistency represents 1 to 5% of the image being misclassified, which is an area between the sizes of the green and cyan squares. A significant inconsistency represents 5 to 10% of the image being misclassified, an area between the size of the cyan and magenta squares. And finally, an extreme inconsistency represents more than 10% of the image being misclassified, an area larger than the magenta square. It is important to note here that the magenta square is more than 5 times the size of the car that was added to this image. This indicates how these inconsistencies at this size could quickly become safety concerns. In order to test the performance of our mutations, we generated 150,000 mutations, which were tested on 5 state-of-the-art perception systems, resulting in 750,000 total tests. From these 150,000 mutations, we found 883 mutations that led to just over 1,200 inconsistencies. These are both just a fraction of a percent, which is good. These are state-of-the-art perception systems, and we expect for them to perform well in the overwhelming majority of tests. This highlights the importance of our mutations to search out the rare but impactful test cases that uncover these failures. On the far right of the graph, we can see our mutations uncovered 20 extreme inconsistencies. Let's look at one example now. In this case, we see the performance of the efficient PS perception system for a scene in which a white truck is entering an intersection. Before the mutation, shown in the upper left, the perception system correctly identifies the truck using the dark blue class. Then, the mutation adds a car in the intersection just in front of the truck, as shown in the upper right. The performance of the perception system on the mutated image then falls drastically, as shown in the lower right. Although the car is correctly classified, the truck is now partially classified as gray, meaning building, and black, indicating that the system does not know what it is. This is a potential safety hazard if the perception system believes that there's only an unmoving building ahead instead of a large vehicle entering the intersection, as we can imagine that these 2 scenarios would lead to very different actions by the vehicle. Now let's examine the performance of the different mutation types in testing the perception systems. On the right, we see the number of inconsistencies found by the mutation for changing the color of the car. On the left, we see the number of inconsistencies found by the mutation to add the car to the scene. Even though changing the color of a car and adding a car to the scene both affect the same number of pixels, meaning 1 car's worth of pixels, adding a car to the scene yields far more inconsistencies. This highlights how increasing the semantic coverage of the perception system through these mutations to create substantially different scenes is a powerful tool to advance testing of these systems. Finally, we need to talk about false positives. As we have discussed already, although we set out with the goal to leverage existing real data to ensure we generate realistic test cases, sometimes the mutation process introduces false positives. For example, the case of the intersecting truck and van that we saw before. To combat these, we must balance the trade-offs of allowing more varied mutations at the expense of also generating more false positives. This pipeline has a relatively high false positivity rate, which sets future directions of research to understand how to improve the mutation process. However, these false positives come at a relatively low cost, as it takes only a few seconds for a developer to examine these test cases to determine if it's a false positive or not. Please see the details in our paper for more information on false positives and our strategies to mitigate them. While we have talked before about how false positives can arise from unrealistic data, I want to highlight how sometimes it can be difficult to decide what it means to be realistic. For example, consider this red car that has been mutated into a blue car that we saw earlier. This is a very realistic blue car, except for one thing. The mutation operation did not understand the difference between red paint and red brake lights, and so the blue car ended up with both blue paint and blue brake lights. Now, this is physically possible to build a car with blue brake lights. However, many regions have laws that govern brake light color, and non-red brake lights would not be allowed. This highlights how determining what constraints are important in checking realism can be domain dependent and will require further refinement in future research. In conclusion, we introduced the notion of local semantic test case mutation that allows us to leverage existing annotated real-world data to generate realistic and novel test cases to expand semantic coverage of perception systems. Our experimental results have uncovered significant failures in state-of-the-art perception systems and lays the foundation for future research into semantic mutation. Our long-term vision is a time when autonomous system testing is measured not by millions of miles driven, but by semantic coverage of real scenarios, including rare but safety-critical conditions. Thank you.